Hi, Constance. Can you hear me? Okay, good. All right. I don't know if you saw my email. Where I live, we're having a bad storm, but I think it's passed, so I think we should be okay. We lost power briefly, but it came back along with the internet, so I think we're okay now. Okay, yeah, I just was worried. It happened one time when I couldn't do the chat because I couldn't get on the internet. So I think I'm okay now, though. So let's go ahead and get started because it takes time to go through the prep quiz. I don't know if any other students will join us, but hopefully we'll have some more students. So I posted a copy of the prep quiz, and we're going to go through it. And I wanted to mention some of the questions need a little bit more working out. So I have what I call a detailed solution handout, and I'll post that after the chat. All right, so let's go ahead and get started. So if you remember, we started out with the linear and exponential functions and the regression analysis in Unit 3. And so some of this is just graphing. So the point whose coordinates are 2, 7 is located in what quadrants? Just a little bit of definition review. So you want to try that one? Yep, that's in quadrant 1. Good. And then a simple plot the point. I'm just going to go ahead and do this one. So it's 3, 5. We start at the origin. X is 3, Y is 5, and it looks like it's choice D. Make sure I pick the right one. Yeah, it's D. And then the opposite, give the coordinates of 2 points if they give you the graph. So again, just a little bit of review of graphing. So point A here is going to be 7, 4. 7, 4. So I've got 2 choices now. And I always like to tell students just try to eliminate. So we could eliminate those 2 because they don't have the right A point. And then B is negative 4, 6. And so it looks like our answer here is D. So these should be pretty easy. Yeah, you've got them. Okay, this one, I think I have detailed solution for it. Hold on a second. Question 1, question 2, question 3. No, I don't. Okay, this is a pretty easy one. So is this point a solution? Yeah, you don't even need to do this one. Is the point 3, 8 a solution to this? So if I put in 3 for X and 8 for Y, do I get a true statement? And this one I do. So this is a pretty easy one. That's a yes. Okay, we have more people coming in. Good. All right, same thing on this one. Is the ordered pair a solution to the equation? And this time I gave you the ordered pair 3, 2. So if you look here, it says X minus Y. So 3 minus 2 is 1. 1's not equal to 9. So this is not a solution. Okay, some special graphing. So anybody remember the graph of X equals negative 1? What kind of a graph is that going to be? Remember, this is one of the special cases. Is this going to be a vertical or a horizontal line? Anybody remember? If it's an X equal, is that horizontal or vertical line? Everywhere along the line, X is going to be negative 1. No, it's actually a vertical line. Horizontal is a Y equal. Okay, so this is a vertical line. Actually, you can see from the answers here. And it's X equals negative 1. Yep. Everywhere along the line, X is negative 1. So let's take a look. It must be D. Yep, it's D. So remember that. So if it's a Y equal, so if it's something like Y equal 4, that's going to be a horizontal. And if it's like we just did, X equal negative 1, that's going to be a vertical. Okay, so there's what we call the special graphs. Let's see, this one is graph the equation. Yeah, I think I have a detailed solution for this one in number 7, so let's pop over here. Oh, I don't. Wait a minute. Yes, I do. There we go. All right, so if I want to graph this, I need to find some values. And so I could put it in slope-intercept form if I wanted. I just pick some values and solve for Y. So if I let X equal 0, if I put in 0 for X, I got negative 1 for Y. And then I let X be 2, and I got negative 2 for Y. And then I let X be negative 2, and I got a 0. So I've got 3 points. And then you want to take a look at the graphs. If you wanted to, you could put this in slope-intercept form, and that might be easier for you. It depends on how you feel about it. So let's take a look at the graphs. I've got 0, negative 1. So let's take a look. 0, negative 1 is not on this graph. So if I did my finding points correctly, it doesn't look like it's on that one. Looks like it's on this one. It might be the only one. 0, -1. Let's check the other points. 2, -2. 2, -2. Yep. And -2, 0. Yep. So the answer there is B. So it's actually not that difficult to do those. All right, so that was B. Let me circle it over here. Okay, let's see what else we did. Find the x and y intercepts for the graph and then graph it. So I've got a detailed solution for that one too. Okay, so when you want to find the intercepts, for the y-intercept you're going to let x be 0. So I took the equation and I put x equals 0 in and I got y is -4, so there's one intercept. And then for the x-intercept I let y be 0 and solve for x. In that case I got x is 4/5. So this is where the graph is going to cross the y-axis and the x-axis. So let's take a look. Well, first of all, look and see. They gave you the intercepts. So the first thing you want to do is see if you got which one has the answers you got. So 0, -4. This looks like a good one here. This one doesn't look good because it doesn't have the intercepts I found. And again, by process of elimination, it has to be this one. Let's just check and make sure. Let's see, 0, -4, 0, -4, and 4/5 is approximately here. So this is the right answer. So again, you can, by process of elimination, get the answers on these pretty quickly. I don't think you'll have trouble with these linear graphing ones. So that was an A. Find the slope of the line between the 2 points. All right, I've got a detailed solution for that one. I'm going to have to do a little work on that one. All right, so pick one point to be point 1 and one to be point 2. Set up your equation for slope, change in y over change in x, rise over run. So the way I set it up, I have 1 minus 1 is 0 over -7 minus 9. I get 0 over 2. The slope of the line is 0. So that would be, what kind of a line? Anybody remember? If the slope of the line is 0, that's one of those special lines. Is that a vertical or horizontal? Good review question. Anybody remember? If the slope is 0, what kind of a line? Is it vertical or horizontal? It's a horizontal line. Undefined is the vertical line. But if the slope is 0, if we were to graph this line, it's going to be a horizontal line. Everywhere along the line. In fact, you can see here y equals 1. So actually, I can do a quick little graph too. Let me change the color. Oops, wrong one. I'm going to get a different color. Uh-oh, Justine got knocked off. She might have bad weather where she is. So y equals 1 would be somewhere here, like that. Okay, so that would be slope equals 0, horizontal line. If the line is vertical, like the one we just did before, like this is undefined. So let me draw a line. This is undefined. This is slope equals 0. Good review question. All right. Find the equation from the graph. Question number 10. I think I have a detailed solution for this one too. Oh, no, I don't. Okay. I'll do it by inspection. Okay, the first thing to notice on this line is it goes through the origin. So we know there's not going to be a b in the equation because the y-intercept is actually 0, 0. And then what I can do is figure out the slope of the line by inspecting the graph. So when x goes up by 1, y goes up by 3. X goes up by 1, y goes up by 3. So the slope of the line, first of all, notice 2 of these have negative slopes and this has a positive slope. So I can eliminate this one and this one because they're giving me negatives. And the actual answer is right here. Because the slope of this line, remember, rise over run. Rise is 3, run is 1. Y goes up by 3, x goes up by 1. So the equation of that line would be y equals 3x. Okay, definition question. A special type of relation where each value of the independent variable corresponds to a unique value of the dependent variable is called what? Now we're getting into section 610 that we went over. Is that a range, a relation, a function, or a domain? Anybody remember on that one? No, this is a function. Okay, the range are the values that y takes, and the domain are the values for x. The function is the relation, and it's a special one. Remember, we're going to do a vertical line test in a minute. When it's a function, for every independent x, there's only one dependent y, and that's a function. Here we go for the vertical line test. So determine whether the graph is the graph of a function. Remember that vertical line test? Let me get my color up here. So if you drop a vertical line, if it only crosses the graph in one place, does that make it a function or not a function? Anybody remember? The vertical line test. If it only crosses the graph in one place, no, it is a function. This is a function. And what that means is for every value of x, there's one and only one value of y, and that's why the vertical line test works. If you remember, we had some, I know I had some examples in the homework, things that look like this. And if you drop a vertical line on that, it's not a function, because for this x value, I could either get this y value or this y value. Okay, so this is not, and this one here is. Vertical line test. Evaluate the function for the given value of x. So, this is a pretty easy one. Here's the function. They want you to evaluate the function when x equals 8, so you're just going to take 8, put it into the function. 8 plus 3 is equal to, anybody want to try that one? That's a pretty easy one. 8 plus 3 is equal to 11. Pretty easy one. All right. Number 14. I actually do have a detailed solution for this one. It's still pretty easy. Evaluate the function when x is 3. So you're going to take the function, put in 3 for x, simplify. So I've got negative 15 minus 9 gives me negative 24, which is answer B. Okay, so these shouldn't be too hard. B. All right, so somebody brought this up before. Find the domain and the range. It says graph the exponential function and then give the domain and the range. So let me pop over here because we have to do a little bit of work on this one. So the first thing I did was pick some x values and find the y values so I get an idea of what this looks like. And it's y equals 4 to the negative x. So I put in first a 1. I'm sorry, I put in 0. So 4 to the 0, any base raised to 0 is 1. Then I put in 1, so that becomes 4 to the negative 1 or 1/4. Put in 2, I get 1/16. When I put in negative 1, etc. I want to get an idea what the graph looks like. Okay, so let's take a look at what we've got here. So we've got 0, 1. So when x is 0, it should cross right here, which this one does. So this is a possibility. This one's not. So again, process of elimination, you can probably throw out several answers. You can throw out this one. All right, so we're left with 2 here because both of these graphs are crossing the y-axis at 0, 1. So now what happens here? So when x is 1, what happened to the y value? So when x is 1, the y value didn't go up, it went down, didn't it? So I have 0, 1/4, and then I have 2, 1/16. Let's look at this one. So here we have the 0, 1. Now when we get to x equals 1, it's getting smaller and smaller and smaller, which is what I see happening here. Let's look at the negatives. At negative 1, we had a 4. Negative 1, we have a 4. Negative 2, we have a 16. We can't see that on here. But the correct graph here is D. Okay, I thought I saw a question coming in. And then the domain and the range. Let me just review domain and range. Catherine had a question. The domain means, let me just put this up here for you. This is x. Oops. Domain is x. The range is y. Oh, sure. Let me just finish this one. So the domain means x. Most every exponential you're going to see is going to have the domain of all real numbers, negative infinity to positive infinity. The range is the y values. And if you notice this graph, it approaches the x-axis, but it never crosses it. So it's all positive values. Okay, so Catherine, tell me a question with a fraction. Do you mean for an exponential function? Okay, but tell me what you mean by a fraction. I don't know what kind of question you mean. Question 14. Okay, let me go back. No, I think you might mean back here. Like this one. Okay. So how did I get the 4/5? Is that your question? So what I did was I let y equal 0. I wanted to find the intercepts because it said find the x and the y intercepts. So to find the x-intercept, I let y equal 0. So I took the equation and in place of y I put a 0. And then, let me move it over here, I added 4 to both sides. So I started with, let me start again. Let me go up higher. So I have 5x minus 4 equals 0. And then I'm going to add 4 to both sides so I can isolate the variable. So minus 4 plus 4 equals 0 plus 4. And then on the left side I've got 5x equals 4. And now I'm going to divide both sides by 5. So 5x over 5 equals 4 over 5, or x equals 4/5. Does that make sense? So you see how I got that from my x value here? Well, you're not really graphing it. They're asking you to find the intercepts. It's going to be between 0 and 1, closer to 1. So if you think, it's hard to see on here, but if you think about that tick mark being one whole unit, this is 4/5 of it. So when I looked at my graph here, I said, well, the line is going to be close to 4/5, but it's not going to, I'm not going to actually be able to get there because it's of the quality of the graph. So it's going to be an approximation in this case. And remember, on the final, you're not going to be actually graphing it. You're going to be given multiple choice options and then pick it. One of the questions from the test had a fraction and top ended up being x and bottom y. I'm not sure. You mean on the prep quiz? Because there's pools of questions. You're going to get different ones when you take it over and over again. Oh, Unit 5. Okay, it's possible. If you want to send me an email afterwards with the question number, I can, if you're having trouble with it. Okay. Justine, you're always going to use 0 if you're trying to find the intercept. So if you're trying to find the y-intercept, you let x equal 0. If you're trying to find the x-intercept, you let y equal 0. And this particular question asked you to do that, and that was part of the answer up here. These were the intercepts. That's why we did it that way. Okay? And then, Catherine, if you email me that one, I will help you with that for sure. All right, let's see. We just did this one. Hold on a second. Let me bring the answer over. Oh, don't need that yet. $14, $15. This is my detailed solution one. Okay, so the answer on that one was D. So let me just write that over here. This was D. Alright, and then let's see. An economist predicts the buying power of a dollar X years from now will decrease according to this formula. This is an exponential. How much will today's dollar be worth in 4 years? And they give you the function right here. So let's pop over here. And so what you're going to do then is you're going to substitute in the value they ask you to evaluate. They said in 4 years, what's the buying power of a dollar going to be? So in this equation, X is 4. So in my calculator, I take 0.87 and raise it to the 4th power, and I end up with 0.5729, or about 57 cents. All right, so that's an application of the exponential. So we didn't do a lot with, you're not going to be tested a lot on it, but you will want to be able to recognize an exponential graph and then also evaluate an exponential function. Okay, now this is 12.6 on correlation, and here's a definition question. The value R, the correlation coefficient that represents the strongest negative correlation, is what? So which of those 4 answers there is the strongest negative correlation? Anybody want to try that one? Strongest negative. Yeah, -1. Yep. Okay, and then interpreting a little bit of a graph here, determine if a correlation exists between the quantities, and if so, how strong is it? So here's the graph. So first of all, the direction here we say is what? Positive or negative? It's going to be, well, the first question is there correlation? And there is. Remember, it's negative, yes. And is it strong? Let's look at our negative choices. We have weak or strong. What do you think that is? Anybody want to try? Yeah, this is strong. Yeah, it's definitely strong. Okay, here's where you're going to use the table. You will have the table available to you, and I've got it up here too so we can look at it. So this is where they give you the correlation coefficient, they tell you the sample size, and they tell you the significance level, and they want to know if there's significant linear correlation. So we've got n equal 5 at 0.05, and our correlation was 0.223. So here's your table. So you're going to look at the 5 row, and you notice that the correlations have to be pretty high here in order for us to have significant correlation, 0.878. Ours was only 0.223, so in this case there is not significant correlation. Does that make sense to everybody? And again, you're not going to have to do the calculations, you're going to be asked to interpret just like you're seeing here. Remember on your homework, sometimes you had to do a correlation calculation, but we're not going to have you do that on the final. But I will have you do a scatter plot, and I'll give you the data, and then I'll say which scatter plot is it. And I hope these are the right ones, because we had trouble with these before. Let's take a look and see. All right, so here's my points, and let's take a look and see if we can pick out the right graph. So the first point is 2, 5, 2, 5, 2, 5, 2, 5, 2, 5. Okay, so that's on all of them. I always like to go to the highest one then, 10, 16. So 10, this doesn't look like 10, 16 here, does it? I'm going to throw this one out. That doesn't look like the right one. 10, 16, that doesn't look right either. 10, 16. Or 10, 16. This looks like a good one here, doesn't it? 10, 16. Let's check some of the other ones. 5, 10, 5. Yeah, these graphs are messed up again. 5, 10. What's the highest one? 10. Oh wait, this is 10, 16. I'm sorry. Let me go back. Let me erase this for a second. This one looks alright. 10, 16, 9, 12. This is actually the right one here, I think. I always have trouble looking at these online. 2, 5. What do we have next? 5, 10, 6, 8. This is it here, right here. Yeah, 9, 12. This is the right one. It's hard to see these online. This is not right, and this is not right if you start matching up the points. So the correct one on this one is C. Let's see. Okay, now we're going on to graph theory. All right, an edge that connects a vertex to itself is called what? Definition question. What do we call that? An edge that connects a vertex to itself is called a, anybody remember? What do we call that? Anybody remember? That's a loop. Loop, yep. Is this graph connected or disconnected? Connected or disconnected? No, this is actually disconnected because you notice where these edges are crossing one another, there are not vertices here. So this is a disconnected graph. And let me just go back for a second. A circuit is not an edge that connects a vertex to itself. Remember, a circuit is a definition of going through the graph. We're going to get to those in a minute. All right, so here's a graph. Are there any bridges? Any bridges? Remember, what does a bridge do? When you take an edge, if an edge is a bridge, when you remove it, you get a disconnected graph. So are there any bridges here? I can see an easy one right here. BC is definitely a bridge, right? Because if I take that out, I've got two parts to the graph. Is there any other bridge? Yeah, BC definitely. Any others that would create a disconnected graph? There's one more right here, AE. Because if I take this edge out, vertex A is no longer connected to the graph. So the correct answer is going to be A. If a connected graph has exactly two odd vertices, A and B, it should say each Euler path must begin at vertex A and end at vertex B, or, remember it's going to have two, what would the other one do? Remember this one? So if you had exactly two odd vertices, you always would start at one and end at the other, or start at the other and end at the other. So what would the right answer on this one be? This is going to be, so first we started at A and ended at B. The opposite is going to be start at B and end at A. So this would be the other option. And that's your Euler's theorem. So using the following graph, find a Euler path that starts with vertex A. Now remember, the difference between the path and the circuit, when we're doing a path, a circuit has to start and end at the same vertex. A path does not. Alright, so let's take a look at the options here. First question is there going to be a Euler path? There is, because, excuse me, there are odd vertices here, so we want to think about that. So let's take a look. Let's try the first one listed here. A to C to D to A to B to D. Euler path goes through every edge. How about these? Oh, well, this one doesn't even start at A, so we could get rid of that one. Here's your process of elimination again. This is not even the right kind of an answer. And then this one is AB, D, C. Okay, that doesn't hit all the edges. So the correct answer on this one is B. Okay, use of the following graph, find a circuit that begins and ends with A. So the first thing you want to take a look at is, are they all beginning and ending with A? And it looks like they are. So let's take a look and see. First of all, is there a Euler circuit here? So how do you determine that? Look at your vertices, right? A is odd. There's one odd. B is even. Let's start jotting down. So it looks like A, looks like A is 1, 2, 3 is an odd. B is even. How about C? Take a look. What's C? 1, 2, 3. So C is odd. And then we need D. How about D? D is 1, 1, 2, 3, 4. D is, oh, sorry, my little pen doesn't want to go in there, even. And then lastly, we need E. So my question is there even a path there? E is even. What do you think? Is there going to be one? What did Euler's theorem tell us? Oh, shoot, I can't get back in. There we go. That was odd. What did Euler's theorem tell us then? Is there going to be, if there's two, we have two odd vertices there. So what does Euler's theorem tell us? What does it say? It says if there are two odd, there's at least one path but no circuit. So there is no circuit for this one. There would be a path, but not a circuit, because there's two odd. What makes what odd? The vertex? The vertex is odd if it has an odd number of edges connected to it. A is odd because it has 1, 2, 3 edges coming to it. C is odd because it has 1, 2, 3 edges coming to it. B is even because it only has 2 edges. D, we said, was 1, 2, 3, 4, was even. Okay, so once you know there's two odd, you know there's going to be a Euler path, but not a Euler circuit. All right. For the following floor plan, is it possible to find a route that begins in one room, passes through each doorway exactly once, and ends in the starting room? So let's say, for instance, we start here. So we could go here, 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 here. Could do that, right? So it looks like the answer for this one is yes. Okay, the method discussed that would determine an approximate solution to a traveling salesman problem is called what method? Remember, we had a way to get an approximate solution because sometimes it gets crazy when there's lots of vertices in the problem. This is called, no, this is actually the nearest neighbor. Okay, brute force is where you do all the different paths and figure out the cost or the distances. Nearest neighbor, remember we started and we said we went to the closest and the closest, called nearest neighbor method. Find two different Hamilton paths for the given graph. Now, what's the difference between a Hamilton path and a Euler path? Who remembers that? Remember, a Euler path or circuit, we're talking about edges. When we talk about Hamilton, we talk about going through the vertices. So we want to find Hamilton paths, not circuits now, for the given graph. So let's take a look at what they give us here. How about A, E, F, B, C, D, H, G. Hits all the vertices, so it looks like a good one. And then what's the other one they gave us? A, E, F, B, C. This one goes the other way over here. So A looks like a good possibility. Take a look at the others here. This one's no good because look what it does. It goes E, A, and then it comes back. It's going through this again. Remember on Hamilton, we go through each vertex one time. And then how about the last one? C, G, H, D. Again, you don't even have to track these. You can look at them in the descriptions here. This goes through C twice. So the correct answer here is A. Okay, so Hamilton path. And a path doesn't have to start and end at the same vertex. Find two different Hamilton circuits for the given graph. It's a little hard to see this picture, I know. Okay, so now we're doing a circuit. All right, so the first thing to look at in the answers, are there any that are given there that are not circuits? So let's take a look. A circuit has to start and end at the same vertex. These are not circuits here. A to C, C to, now that one would be, but one of them is not. We can eliminate that one. It will have two different ones. How about this one? This goes B to B, D to B. Can eliminate that one. Looks like we're left by default with the last one, and let's just check and make sure it's correct. So it goes C, E, C, E, and then it goes to D, F, G, H, B, A, C. Hits all of them. And then the other one is C, H, B, G, F, E, D, A, C. Ends at the same. Remember, if it's a circuit, it has to start and stop at the same vertex. Okay, Lori drives a parcel delivery truck. Her route consists of 8 stops. How many ways can she travel to the stops and return to her warehouse? Now, got to be careful here because the warehouse is a stop that's not already been included here. So actually, in this problem, the number of vertices, if we were to make the graph, would be 9. And what's the formula for the number of, basically we're talking about Hamilton circuits. Anybody remember? What do we do, the formula for finding the number of Hamilton circuits? Anybody remember that? It was number of circuits was equal to n minus 1 factorial. So in this case, that's going to be 9 minus 1 factorial, or 8 factorial. And if you do that on your calculator, 8 times 7 times 6, so forth, it's 40,320. And don't forget to put the starting point, add it to the number of stops, because students get confused and think there's only 8, but there's actually 9 if you were to create the graph. There would be 9 vertices. All right, definition question. A connected graph in which each edge is a bridge is called what? Remember that one. A connected graph in which each edge is a bridge is called what? Remember the definition of a bridge. If we take it out, we create a disconnected graph. This is a special kind where every edge is a bridge, and that's a tree. All right. These are kind of fun. We want to pick the right picture. So use a tree to show employee relations in the auto parts company. President Richards has 2 vice presidents, Greenberg and Marley. Okay, good. Okay, so Richards has Greenberg and Marley. Greenberg and Marley. Greenberg and Marley. Now look at D. D doesn't show the Greenberg reporting to Richards, so we can probably eliminate that one. Greenberg is in charge of 3 regional managers. Greenberg, Reynolds, Hahn, and Johnson. This is not showing them reporting to him as the boss, so this one we can eliminate, because this one looks like Johnson reports to Reynolds, reports to Hahn. let's see, this one looks good here. Marley's in charge of 2 regional managers, Croft and Smith. Croft and Smith, that looks good. And Croft and Smith. And then Smith has an assistant, Lowell. Okay, so on this one, it looks like Lowell reports to, what's his name? Marley. This one over here shows that the assistant is going to Smith. So this is the correct graph right here. Those are kind of fun to do, I think. Okay. Find the minimum cost spanning tree for the graph. And I don't think I did a detailed solution. That's what I was looking to see. Okay, so what do we do on this one? Remember, this is where we were finding the minimum cost spanning tree. Where do we start? We start with the cheapest or the shortest distance. I don't know if these are prices or distances here. So let's take a look. Where's the shortest one? It's right here, isn't it? It's actually kind of nice on here because I can fill it in with colors. Let me get the red. All right, so we're going to start here. All right, where are we going to go after that? We see a 9 and then we see a 10, right? So we could go next to the 10. That would be okay, right? Because the one thing you want to make sure on this one is that you don't make a circuit when you start filling in and picking, which means I don't want to pick 11 because that would give me a circuit here, which I don't want. So I'm not going to do this one. I've got 9 and 10. Okay, what would come next? What's the next shortest one here? 13. And then what's next? 16. Now again, I don't want to pick 17 because I would create a circuit here and that's not getting me anything. I could do 18. Oh, you know what? I missed one actually. I missed the 15. I do want to do this one. Should have done that one earlier. The 15 is a good one. Let me go back. Let me get these off of here for a second before I went there. I should have done the 15 here. I missed it. The 15 would go next. Okay, because then I'm not going to need the 18. So what's next after this is, and we did have the 13. The last one I need is the 16. So if you notice now, I've connected all the vertices exactly one time with the shortest distances. So I did this and this. Then I actually went here. Then I picked up the 15, and then the last one I needed was a 16, and I'm done. 1, 2, 3, shoot, this way, this way. Everything's connected. So which one is it? It's not this one. It's not that one. Looks like it's D. Okay. Okay, so now we're into the last unit. This is where we did the voting and apportionment methods. Catherine, did you have a question? Okay, go ahead. Okay. I don't need 18. Okay, I don't need 18 because let's go back. When you do this, what you want to do is you want to have everything connected. You want to have all the vertices connected in some fashion with the minimum cost or the minimum distance. So where you start is with the cheapest one. In this case, it was the 9. Everybody agree on that one? And then the 10. Now, I don't want to go to the 11 because then I'm creating a circuit, and I don't want that. I don't want things connected that way. All right, what's next? 9, 10. I'm not going to do 11. Then the 13. And then I went to the 15. Now, everything, I've captured everything. The only thing I need to do is pull this part here and connect it, and that's where I did the 16. I don't need the 18 because everything's connected now. I could go from here to here to here, here to here, here to here to here. Think about something like this. Think about running internet wires, let's say, and we want to connect all the classrooms at a college. We don't want to connect them twice. We only want to connect them once. I don't need this because everything else is connected. So I don't need to connect here. If I connect here, I'm adding cost. So think about, there's a nice example in the book, I think I did it in the chat, where at a school they were trying to cover the pathways where students walked. So they only wanted to make sure every pathway was covered, even though it might not be the the most direct route, in terms of cost, it's cheaper to just make sure everything is connected together at least one time. And that's where it matched up with this answer here. We don't need the 18 because all the other vertices are now connected. And they're connected in a minimum cost tree. Remember, in a tree, if I take any edge out, I create a disconnected graph. And it doesn't always look like the most logical route, I know that, but it's cheapest, or it's the shortest distance, either one. Okay, so now we're in the last unit. Using pairwise comparison method, the number of comparisons needed when there's n candidates is determined by which formula? Anybody remember that one? What was the formula that we used? Yeah, it's B. Yep. Okay, all right, I've got a detailed solution on this one, number 36. Get a little bigger. All right, they want you to use the board account method. And so what I did, remember board account, we've got 4 levels. So first place is 4 points, 3 points, 2 points, 1 point. And I go through and there's states here, places for vacation. So I did Alaska first. So I figured out how many Alaskas were here. There were 17 altogether. 17 times 4 is 68. Second place, there were none. Third place, Alaska had 15 times 2, and Alaska had 10 in third place. And so what I did in each case, I think you all know how to do these, figure out how many points. Whoever has the most points wins, and in this case, it's actually Florida. So if you work through, and then it also wanted to know if the winner received a majority of the first place votes. And I don't know if I answered that one. Florida had first place votes 12 out of 42, 29% is not a majority. So the answer here is Florida, and I'll let you check on those if you want. So that's a board account method. A voting method that always satisfies the majority criterion and the head-to-head but may not satisfy the others is a definition question. Which one always satisfies the majority and the head-to-head but may not satisfy another one? Remember? Yeah, this is the pairwise method. Yep. Yep. The mathematics department held an election for a chair. Here's the results. If we use board account, is the head-to-head satisfied? So let's go over here. Okay, so if I do the board account on this one, there's 3 choices. So 3, 2, 1 for the points. So Clark has 8 first place votes, 4 second place, and 17 third place. Here's his total. Here's Jones. Here's Smith. So Smith won by board account. Head to head, we have to compare 1 by 1 here. So Clark versus Jones. Jones got a point. Clark versus Smith. Smith got a point. And Jones versus Smith. Smith got a point. So Smith won. Smith won. So this board account method also satisfies the head-to-head criterion. Yes. It doesn't always. Remember on the board account, that was one of the questions on the discussion last week. So that one's a yes. Okay, the same scenario in the same data table actually. Now they want to know if plurality is used to determine the winner and then Clark drops out, is the irrelevant alternative criteria satisfied? Okay, so plurality first. If we start out first, we have Jones with 11, Smith with 10, and Clark with 8. So Jones won by plurality. He had the most votes, or she had the most votes. Okay, Clark drops out. So you're going to go across the table and you're going to take Clark out of each column. And here's my new table. So now the plurality method, Smith has got more first place votes. So the irrelevant criteria is not satisfied in this case. Remember it said if somebody drops out, the original winner should still win. So in this case, it does not satisfy the irrelevant alternatives criteria. So that's a no. The rule stating that an apportionment should either be the upper or the lower quota is called the... I remember that one? It's pretty easy actually. It's the quota rule. Okay, and now let's get into some apportionments here. Actually, just find a standard divisor. And I think I've got a detailed solution for this one yet. So how do you find the standard divisor? You need the population total. It wasn't given to us, so I had to add the numbers up. 1569, and then divide by the number of items to be allocated, which was 39, so the standard divisor here is 40.23. And then let's just stay over here with the next question. Whoops. They want you to find a standard quota now for one precinct. So the first thing I need is the total, which wasn't given, so I added them all up. And then I need the standard divisor. So I take the total and divide by the 40, and I get 641.575, and they wanted the standard quota for the third precinct. So I took 3117 divided by the standard divisor, and I got 4.858, which rounds to 4.86. I think that was one of the answers. 4.86, yeah. Those are pretty easy. Okay, modified quota. I think I have a detailed solution for this one too. So what does modified quota? They gave us the 27 here. We don't have to really do much work except to take that particular category, which was civil engineering, take 153 and divide by 27, and I get 5.67. Modified, because we didn't use a standard divisor. Okay, so 5.67, which is B. And, okay, definition question. Hamilton and Jefferson's methods favor which ones? They favor northern states, southern states, large states, small states. We could sort of eliminate these, right? Doesn't make a whole lot of sense. What do they favor? Hamilton and Jefferson favor, anybody remember? They favor large states. Okay, and then the last one is about a paradox, population paradox. So let me jump over here. All right, so what do we have to do? Remember this one, because they gave us 2 different years, and we have 160 seats in 7 states, and what happened over the time period is the population went up. So what I did was I did my allocations in 1990, down here. I got the lower quota. I used the Hamilton quota. Remember, we see how many we didn't allocate 3, so we had 3 left over. So I give those to the states with the largest decimal, which was 1 here, here, and here. So they got the extra items. Then we take a look at the allocations in 2000 by the same process, and then we look to see. Population paradox says, did anybody gain or lose, and where do we have changes? We had a change here, here, and here. Actually, this one stayed the same. These are the 2 we need to worry about. Okay, they both lost. Actually, I did all the changes. So how does the population paradox occur? It occurs if what? If somebody loses a seat to somebody that was growing slower. So let's see, anybody lose a seat? This one lost a seat. It stayed the same, stayed the same. This one lost a seat. This one gained a seat. But this one's growing faster. So that would make sense. So this is not an example of the population paradox. If this growth rate here had been less than this growth rate, then it would have gained a seat even though it wasn't growing as quickly. So in this case, the answer for this one is no. A little bit of work on that one to get to the answer. Okay. A couple people came in later. I'm going to post these detailed solutions afterwards. So if anybody wants to take a look at those, you'll have those available to you. This was a no. Okay. Questions. So that was the prep quiz. You still have access to it. You can take it over and over again. You get different questions. This has more questions that will be on the actual final. So I can't remember how many yours has. Probably 35, I'm guessing. Probably has 35 questions. All right. So any questions from people who are still here? We have a couple people still left. Only 2 people left. Catherine and Constance, any questions? Oh, you're welcome. Okay. All right. And Catherine, I think you were the one with the question from the Unit 5 test. If you want to send me that through my courses, I'll take a look for you. Okay, great. All right, ladies, well, have a good evening. Good luck on the final. Final grades will be posted Monday, and you can still take the prep quiz through tomorrow night if you want to still practice. So Good luck, everybody. We're almost done. Have a good night.